Hello, in this video I'm going to work through another application problem from homework number 9 on MathXL. This one happens to be number 5, and number 5 looks something like this. When reacting with water in an acidic solution at a particular temperature, compound A decomposes into compounds B and C according to the law of uninhibited decay. The initial amount of 0.3 moles of compound A decomposes to 0.27 moles in 30 minutes. How much of compound A will remain after 2 hours, and how long will it take until 0.1 moles of the compound A remain? So you may or may not be taking chemistry, and you may or may not have ever seen chemistry before, but it doesn't really matter here. We can perform the mathematics behind it as long as we carefully interpret the description that the problem has provided. So the fact that we're dealing with uninhibited growth or uninhibited decay leads me to recognize one of two different functions. Either the format that I've been using in all of my videos, or the format that MathXL has been introducing in the Help Me Solve This and Show Me an Example question help options. In this video I'm going to work through this particular problem both ways simultaneously, and this will again further reinforce the notion that either method is correct. Well, before we begin, we really should identify some given information. We know that there's an initial amount of 0.3 moles of compound A. So in this example over here, an initial value or initial amount is represented by C. So we have 0.3 moles. And over here, the initial value is A sub 0, and that's again 0.3 moles. We're told that it decomposes to 0.27 moles in 30 minutes. And so we've got to be real careful here. I just noticed that one mention of time is measured in minutes and one is measured in hours. And since our answer or question is asking about some question in terms of, or time in terms of hours, I'm going to treat 30 minutes as 0.5 hours. That's a little bit tricky, but it's a good thing to be aware of. And so I'm going to note that this function evaluated at 0.5 hours is equal to 0.27 moles. And this function, A of 0.5, will result in 0.27 moles as well. So if we need to know how much of compound A will remain after 2 hours, we need to know the growth factor. We need to know the growth rate, or in this case, the decay rate, the rate of decay. And I think we can use that information in both of these cases. Considering that we started with 0.3 and we've only spent 0.5 hours at this, we can actually identify our A value pretty straightforward in this technique. F evaluated at 0.5 will be 0.3 times our A value raised to the 0.5 power. So I've changed the letter x to 0.5. And I also recognize that F evaluated at 0.5 is the same as 0.27. So now we've got the expression 0.27 equals 0.3a to the 0.5 power. I'll divide both sides by 0.3, and I'm not going to reach for a calculator. I'm not interested in the result of this at all, because I don't want to round until the very last step or the final result. I need to isolate the A value, and to remain consistent with the process that I've shown before, I'm going to take a radical on both sides of the equation, and the radical's index has to match the index or the power that's associated with the base of A. So it seems a bit unusual, but it's something that our calculators could handle when we ask them to. And we're going to say that A, our growth rate, is the 1/2 root of 0.27 divided by 0.3. And I know some of you recognize what it means to take a 1/2 root, and that's fine, but let's just remain consistent with the process from before, and we're going to leave this as our a value for right now. In this example, using the techniques introduced by MathXL, we might see the following. A of 0.5 is equal to 0.3 times e to the k times 0.5 power. And k is the value that we're trying to solve for here. Since a evaluated at 0.5 is 0.27, we now have this expression, 0.3 times e to the 0.5 k power. And since we're solving for k is the unknown, e is not a variable, e is an actual number, so let's keep that in mind. We're solving for k, this unknown, we would start the same way that we did in the other example, 0.27 divided by 0.3. Now that we have an exponential with a base of e raised to the power of 0.5k, I'm going to rewrite this exponential as a logarithm in order to isolate this exponent. The base of the logarithm has to match the base of the exponent, and a logarithm with a base of e is written with ln for the natural log. And we evaluate the natural log not at the exponent, but at the result of the exponent, which is 0.27 divided by 0.3, and I'll use parentheses just to be safe. And this is equal to 0.5k. Now keep in mind that there's an implied e here, and if we were to follow our loop rule, e to the 0.5k power must equal 0.27 over 0.3. That's exactly what we had in the previous step. E to the 0.5k power equals 0.27 over 0.3. So now to isolate k, our growth rate, we can divide both sides by 0.5. And k is equal to the natural log of 0.27 divided by 0.3, and all of that divided by 0.5. And that calculation will represent our growth rate. So far so good. We have growth rates in both cases. Now if I were to enter these into a calculator, I would get two different results, but that's okay, because remember, this growth rate here is relative to 1, this growth rate is relative to 0. So let's move on. Let's see how we would use each of these to answer the first question. After 2 hours, the amount of compound A remaining will be how many moles? Well, we've got our growth factor in both cases, and we know our initial value. So after 2 hours' time, our initial amount of 0.3 times the growth rate of 0.5 root, the 1/2 root of 0.27 divided by 0.3, raised to the power of 2, because we're evaluating at 2, now's the time where I would reach for a calculator. And the reason why I would reach for a calculator now is because, again, the instruction said do not round until the final answer, and we're about to produce the final answer. And then we will round to the nearest hundredth as needed. So here we go. Opening up my calculator, we're going to type 0.3 times the 1/2 root, 0.5 root of the fraction 0.27 divided by 0.3. And moving to the outside of the parentheses, we're going to raise all of that to the second power. And I'll press Control Enter because I know I want a decimal. And my calculator displays 0.196. And when we round that to the hundredths place, that's the second decimal, I like 0.20. So 0.20, and we're talking about moles here. And I just realized I've been using the word moles to represent this capital M, and a more appropriate or proper term is molarity. We would say that this compound has a molarity of 0.2. So I'll try to correct that as I move forward from here. But anyway, we think that the solution is 0.2 molarity, a molarity of 0.2. So let's go ahead and use the other form of the equation. We are going to evaluate the amount after 2 hours, and we would like to know the molarity after 2 hours. We hope that we get the same result. Well, our initial molarity was 0.3. Our base for this expression is E. The K, the power for K, is this whole expression, so we're going to try to stuff it in this exponent here. Natural log of 0.27 over 0.3, all of that divided by 0.5. So that number times t, or time in this case, which is 2 hours. And this is an expression that we can bring to the calculator as well. So when we jump out to the calculator, we need 0.3 times E. And we have to use this E key, not the letter E from your keyboard. There is a difference between the two. The K value is a fraction which contains the natural log of another fraction, 0.27. Whoops, let's try that again. 0.27 divided by 0.3. That natural logarithm is being divided by 0.5. And I'll scoot to the outside of that, that set of parentheses, but I don't want to go so far that I'm outside of the exponent level. So I'm here, and then I'm going to multiply by the number 2. And again, this is a little bit hard to interpret, but this 2 is multiplying by this result. It's not multiplying by the result of the entire expression, which is what we want. And now when I press enter, would you look at that? We've got 0.19683, or in other words, 0.20 molarity. Both results were the same here and here. And not only at the point of rounding, but coming straight from the calculator, both results are exactly the same to the extent of their decimals. And to bring this all home, let's go ahead and enter the result in MathXL, 0.20, and I'll tap enter, and the result is accepted. Let's go ahead and finish this out and determine how long it's going to take in order for the compound to reduce to a 0.10 molarity. And notice our answer here is going to be measured in minutes, so we've got to be careful of our timing. So our end result has to be 0.1, and the formula still holds true, 0.3 times 0.5 radical 0.27 over 0.3. And we're trying to solve for x here. How much time is it's going to take? Now keep in mind that when our solution is obtained and we do have a value for x, then that's going to be a measurement in hours. X is a measurement in hours. So we've got to be careful when we report our answer on MathXL. So I'm going to divide both sides by 0.3, and then I'm going to copy the rest of the expression just to clearly illustrate this result when we obtain it. Now that I'm looking for the value of the exponent, I'm going to use a logarithm to perform that task. The base of the logarithm is the same as the base of the exponent. And we're going to evaluate that logarithm not at the value of the exponent, but at the target or at the result of the exponential. And that should tell me what x is equal to. So when I reach for the calculator, I'm going to ask it to evaluate a logarithm with a base. Now I'm going to try something here. Will this let me highlight just a portion of the... Oh no, it's not going to let me highlight just a portion. I think there's some way to do that, but you can copy and paste with these calculators, and I'm not going to spend the time to figure that one out right now. I'll just go ahead and enter it. We want a radical, so we'll press Control and this key. And the radical has an index of 0.5, a radicand of 0.27 over 0.3. And we're going to evaluate this at the fraction 0.1 over 0.3. Let me just double check that I've got the setup here. Logarithm base 0.1 over 0.3. I think that looks pretty good. And now when I press Control Enter, we obtain a result, 5.2135 hours. And without even writing that down, again, because I don't want to round at all, I'm going to let the calculator perform this next step. I'm just going to immediately multiply this by 60. Whoops. Try that again. Times 60. And so this calculator is going to take the precise result from before and multiply it by 60. It's going to include more decimals beyond what's seen here and provide us with a correct and final solution. And there we go. So 312.815179902 minutes. And truthfully, it might even be worthwhile to note that this result from that logarithm calculation is multiplied by 60. Let me just try something here. What if I type 60? What if I type 60 and then multiply it? Now if I highlight this entire group and tap Enter, there we go, 60 times this logarithm, and now press Control Enter. Okay, good. The result is the same as before. So 312.8, and I believe our site said to round to the nearest tenth, so I do like 312.8. 312.8, and now we're talking about minutes since we've multiplied the number of hours times 60. In the alternate form, hopefully it doesn't take much convincing from here, but we'll go ahead and do it anyway. We're looking for a end result or a final molarity of 10.10. And so the expression was 0.3 times e to the natural log of 0.27 over 0.3 divided by 0.5 times t, actually, not x, but t for time in hours. We'll again divide by 0.3, so we've got 0.1 divided by 0.3 equals this expression, e to the natural log of 0.27 divided by 0.3. The copying gets tedious here, but it is necessary. And so I often say that my brain takes a break as I'm copying because I'm not thinking too much while I'm copying information down. Now that I've had my break, let's do some work again. We're going to rewrite this exponential as a logarithm in order to isolate the variable that's sitting here in the exponent. And I know that the logarithm with a base of e is going to be labeled as ln. The base of the logarithm is e, so I'm not going to write that. That's implied there. And we're going to evaluate this logarithm at 0.1 over 0.3. Now that is equal to this expression, the natural log, and the expression is the exponent from before, natural log of 0.27 over 0.3 divided by 0.5 times t. And now to isolate t, we simply need to divide the two. And we have the natural log of 0.1 over 0.3 divided by the natural log of 0.27 over 0.3 divided by 0.5. Can you see why I'm not a big fan of this technique, especially when we're going for precise answers? And let's also keep in mind that this time result is actually going to be measured in hours. So we really should offset this and correct it for a measurement in minutes, which can be done by taking this result in its entirety and multiply it by 60 in order to convert from hours to minutes. So let's see what we get. In this calculator, we need a giant fraction, so I'm going to start with that first. And in the numerator of that fraction, we need the natural log of 0.1, whoops, try this again, 0.1 divided by 0.3 over top of the natural log. Let's see, I don't really need that set of parentheses there, but we want another fraction in the denominator. We want the natural log of one more fraction, 0.27 over 0.3 divided by 0.5. I didn't need that extra set of parentheses because this division bar is taking precedence. It may be hard to see, but this bar is just a little bit wider than this bar down here, and that's what reminded me that we ended up having a grouping symbol around this entire denominator. But if I tap the left-hand parentheses around that, then we can kind of see that grouping has been made. And now I'm going to jump all the way back to the beginning and tap the left-hand parentheses key again. This will group the entire fraction so that when we move to the far right-hand side, I can multiply this by 60 in order to convert our hour computation in the middle to minutes. And when I press Control-Enter, well, wouldn't you know it, we get the same answer as before, 312.8. 312.8 minutes. So the last thing we need to do is convince ourselves that not only do the answers match, but that they are the correct answers that MathXL is expecting us to compute. And 312.8 minutes indeed is selected or is accepted by MathXL. So I realize that there is a lot in this video, but my argument remains the same. Either technique is good and appropriate. Clearly I prefer the example or the technique on the left because the process is just a little bit more simple. The biggest benefit I can think for using the more complicated form is identifying our k value, especially down here if we were to compute that as a decimal. It's a bit more meaningful because it's relative to 0 as opposed to the decimal value here, which is relative to 1. It takes a bit of interpreting. But I'm willing to trade off that interpretation for a little bit more simplified mathematical approach. Hope this video helps you understand the process, and if you have further questions, please reach out to me. I think I've got one or two more options, or at least one more example that I'd like to work through, the Newton's law of cooling, and I'll pick that up in one more video. Thanks for watching.